Okay, so last time we talked about the importance of exploiting the structure of the electronic health records because it reflects a physician's decision process, and the ultimate goal of the last class's talk was that we wanted to connect transformers self-attention with graph neural networks, graph embedding or graph convolutional embedding, and the reason for that, the connection for that is to actually, we have a specific purpose. So as I said, structure of the EHR can be very helpful when there aren't enough data, or when we're dealing with rare diseases, or like when we're in the low volume regime. But it doesn't, as I said, not always EHR has electronic health record, the data set contains the true structure here. And when I say the structure, I usually mean the red arrows here. So sometimes the electronic health records, so sometimes a hospital forces their employees, basically doctors or nurses or caretakers, it forces their employees to input or record why they're ordering certain medications or certain procedures. So there's a field named reason code. Actually, I can show you that. Give me a second. Okay, actually, I should have. All right. Safari. Okay, so I think we've briefly talked about CD. Like for 30 minutes, we've talked about the common data model, CDM, which is kind of a hot topic in hospitals, especially in Korean hospitals these days. So I think I've stated that there are two major players in the CDM domain, which is one is OMOP, OMOP, and another is FHIR here, as I'm showing right now, FHIR, FHIR. So FHIR has a lot of tables, or so they call their tables resources actually. So, but it's the same as relational database. So they're the same thing as RDB's tables. And somewhere here, there's a table called medication request. So this is when a doctor orders a medication, orders a drug. So you click this, and then there's like a lot of descriptions. But basically, it's, as I said, it's a table. So there are a lot of columns. You can you can see them as columns, or you can see them as like sub nodes or child nodes. But semantically, it's the same thing. So there's medication request, and there's of course an identifier. Every single event in the hospital has a unique identifier because they're all being recorded in the database. And somewhere here, there's a field called reason right here. So there's a field or a column named the reason code. And this is exactly what it says. It's a reason or indication for ordering or not ordering the medication. And it can be a diagnosis code. So this is exactly what I'm saying. So there's usually, so when a hospital like installs their EHR solution into their hospital system, and the EHR system meaning basically a relational database, and in America, in the United States, there is a company called Epic, 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 which is like the dominant player in the EHR market. I think they're responsible for more than 50% of the market share in the United States. So Epic goes to hospitals and they sell their EHR solutions, or maybe it's the other way. Maybe it's the hospitals that comes to Epic, the company, and they asked Epic to install a EHR solution into their a hospital system or hospital electronic system, and then they like have a like they discuss the matter, like what kind of interface they want, what kind of RDB schema they want, what kind of information they want to store, and usually the reason tables for ordering stuff like medication orders or procedure orders or lab orders, order related tables usually contain a reason field, so that when something is actually ordered by nurses or doctors, they are supposed to input why they're ordering certain stuff, certain medication or certain procedure. And that reason code is, as I'm showing right now, it can be either condition or problem or diagnosis code, but they're basically the same thing. It's that they need a diagnosis for ordering stuff. So originally, this red arrow it should be installed in the hospital system, but not all hospitals actually, force their nurses or doctors to input the reason code, or maybe they just ask Epic or some EHR vendor to remove that field so that they don't want to bother with it. And even if there is a field called reason code in the hospital EHR system, they doctors or nurses usually just don't really bother inputting accurate reason code. Actually, they just want to get by the system. So as I'm showing right now, physicians or technicians might enter information into the database incorrectly. So because some hospitals, they actually force the doctors or nurses to put reason code into the interface before they can actually order medications, and which is kind of a bothersome process when you're in the ER, the emergency room, or when you're in the very risky situation or emergency situation. You don't really want to bother why you want to order a medication. So they just put anything into the database, like just some random disease, some random diagnosis code, just to order medication or order procedure. So yeah, so this red arrow information, even though this is a very important information, you can't this information is not always available. So if, like, for example, claims data, they do not even have this information, so we don't need to even bother with it. And two, even if they are available in your EHR dataset, it's not always completely trustworthy. You can't really you cannot 100% trust them. So that's the problem. So the motivation is, if a structure information is available, so if that red arrow is available and can be trusted, then you can design a special model to reflect the structure. So in order to leverage that information, that red arrow information, you can either, one, design a special model such as MIME, which I showed last time, or two, you can just use graph convolution networks, or just some graph neural net, GNN, because structure can be represented by adjacency matrix. And as I think I've said this, in retrospect, MIME is a special case of GCN, graph neural networks. It's just it just has unidirectional edges and some special function to fuse diagnosis and treatment. So this is option one. If structure is available, you can either design the model or you can just use GNN. If a structure information is unavailable, it's not available, then you can, what is your option? What can you do? One is actually just to use multi-layer feed-forward network. Just like before, just use bag of features or bag of codes approach. You just treat a single visit as a unordered set of codes, and you just add all of them together. Or you can just, average the embeddings using all the codes. Or maybe you can use a GCN or graph neural network where the adjacency matrix is 1, meaning that everything is connected to everything else. So in that case, actually, if if you guys are already kind of like quick-witted, this and this is exactly the same thing actually. So adding everything together in your visit is the same thing as using the adjacent GNN with the adjacency matrix of ones. I think we have a new attendee. Let's make sure. All right, give me just a second. All right, thank you. I was going to ask to mute themselves actually. All right, well, I think we have all the regular comers. All right, okay, so back to the class. So as I said, adding everything together and using the adjacency matrix of ones is essentially the same thing. You're just treating that everything is connected to each other. So in that respect, if you don't know the true structure, the red arrows or the red edges, then instead of just adding everything together, which is which was option 2. So if structural information is unavailable, you can just like before, you can just simply add everything together just using the bag of codes approach. But can we do better than that? So can we do better than that? And the answer is probably yes. So what the motivation is, what if we start from fully connected graph, then sparsify? So this is your visit structure here. This is your visit structure. So there's a visit node, which sits at the top here. It's the visit node here, the teeth visit. And this is also the same visit node. And then let's say that there were 5 codes in your visit. There was cough, fever, and acetaminophen, which is a Tylenol, and benzonatate, some other medication, then IV fluid. So 2 diagnosis codes, 2 medications, 1 procedure. So 5 codes in your visit. And your initial assumption is that everything is connected to everything else. It's just fully connected graph. And then as you learn, sorry. So you start from a fully connected graph, and then as you learn, as your model learns to do a certain task, like certain procedure, certain prediction tasks, such as heart failure prediction or mortality prediction, as it learns to perform the supervised task, it may pick up in an important connection and just remove all the other like irrelevant connections. So like here, we assume that everything is connected, and as we move to the right, maybe we can find a true structure that is helpful for predicting whatever you want to predict. And so I guess now is a good time to actually talk about the transformer. Right. So transformer is actually just an encoder, or the let me see. Let me just actually add one more. Okay, how do I use my yeah, let me try to open my iPad. Okay, looks like I can annotate. All right, can everybody see the text here? I can see mine, and I think I can also see it from my laptop. So I'm writing stuff on my iPad, but I think everybody else can see the same thing. Okay, cool. All right, so as I said, transformer is just this. Transformer comes from a very innovative paper named "Attention is All You Need," or maybe it's "All You Need is Attention." I forgot. It's just something after Beatles song, actually. So before, in order to process a sequence or to encode a sequence input, was everybody was using either RNN or 1DCNN. So in this case, I am a good boy has a 1, 2, 3, 4, 5, 6 tokens here. 6 tokens here, including the dot or including the period. So if we use RNN, it would look like this. So RNN contains a hidden layer like this. And then you can either actually, so what people used to actually do is just encode everything into the RNN and either take this last hidden layer as the representation of this sequence or of this sentence. But it could be any sequence though. It can be any time series, any text, or any visit sequence, or market stock price sequence, or whatever. It doesn't really matter. It can even be like continuous values. But the important thing is that if there's a sequence, probably one of the, I would say the only option, because people don't use 1DCNN a lot, but still, like one of the two options was to use RNN and then take the last hidden layer as the representation and then put this into the logistic regression or whatever, just so like there's a logistic regression of this. Actually, this should be H. And then this would be your 1.1 or the 0. Or it could be softmix, whatever. And then a bit more advanced technique is to use attention. So let me erase that. So instead of using only this as your hidden, so instead of using your last hidden layer as representation, you actually have another function that calculates, or actually let's go into the full detail. So probably the complete treatment of the sequence is to use a bidirectional RNN. So bidirectional. So it's a bidirectional RNN. So there's one RNN1, which is RNN forward, RNN could be LSTM, could be GR, it doesn't matter. RNF backward. So one RNN forward goes exactly what it says. It goes forward, and RNN backward goes backward, actually. So this is in order to capture the sequence information in both directions. So it's bidirectional RNN. And then you concatenate this two. So you concatenate. So this becomes a single, you treat them as a single hidden layer. So in this case, now you can't actually treat this as your hidden representation. You can't treat this as a representation because you're going both ways. So it's kind of awkward to pick one single hidden layer as your sentence representation. So in this case, you actually do you apply attention mechanism. So you pull this here. So maybe you take 0.2 of this, 0.1, 0.05, 0.05, maybe 0.2. So how many do we have? 3, 4, 6, and maybe 0.4 here. So basically you're multiplying 0.20% of this. You're multiplying 10% of this, multiplying 5% of this, 5% of this, 20% of this, 40% of this, and then you get the final context vector. This becomes your sentence representation or your sequence representation vector, and then you multiply. You can put maybe a sigmoid function here, and then make some prediction. And the thing that decides this percentage, this portion, like 20%, 10%, 5%, 5%. The thing that determines this this ratio is something called attention function. So there should be a separate function. Let's call that function f, basically. So f just f needs to input basically two things. First of all, it needs to accept the hidden layer. So I'm just going to call them hi, and then some other function, some extra information that needs to, if you're predicting certain disease, then maybe it's the final, let me see. Okay, yeah. If you're predicting just a single prediction target, then you don't need the extra information. This could be just a null value. But if you're doing an encoder decoder style, like sequence to sequence, so if you're trying to translate "I am a good boy" to a French sentence, then maybe you need to have a encoder and decoder. So this part becomes your encoder, and there should be like a decoder part that generates a French sentence, and then in that case you need to have both the hidden layer of the encoder, and hidden layer of the decoder, and then calculate the attention function. So basically, the important thing is there's a separate attention function that is responsible for calculating the percentage when you're performing this convex combination. So this percentage changes by input. It's not always 20%, 10%, 5%. Sometimes this could be 30%, this could be like 10%, this could be like 1%. So this is a dynamic, it's like on the fly ratio calculation, and that is done by attention function. So you're actually not only training both RNNs, the bidirectional RNN, but you're actually training the attention function at the same time. So it's an end-to-end training. And so this was a classical style before like the transformer architecture came out. And okay, so I can't. Let me just erase all of this. Yeah, all right. Let me read all this. And just briefly, the 1D CNN, I hope everybody remembers, but 1D CNN, I think I described this when I was talking about how to automatically code the clinical notes into diagnosis codes. So I'm just going to briefly say this. So if we have an embedding of each word or each vocabulary, 1D CNN employs a convolutional filter, but it's not two-dimensional like you would use. Like you would apply a two-dimensional convolutional filter. In the images, you just apply one deconvolutional filter on your text or on your sequence. So there's one deconv here, there's one deconv here, one deconv here, like this. And then again, you do this like this. Oh, all right, like this. And then you repeat this process, and at some point you will have a you'll have a sentence representation at the top of the pyramid, basically. So it's, yeah, and this is, again, if you just have if you just stack not the enough number of times, if you just apply the convolution filter enough number of times, then you can derive the top embedding, which is the representative vector of your sentence. But interestingly, you can also apply attention mechanism on top of this. So instead of going all the way to the top here, going all the way to the top here, what you can do is you just apply the convolutional filter just one time. So this is your embedding, and this is your a CNN output. Then you can employ a separate input in the attention function, just like before. So this becomes your H1, this becomes your H2, H3, just like in your RNN, and then this becomes something here. So exactly the same thing. So you can calculate the attention function, you can calculate the attention score for each embedding or each hidden layer, and then just multiply, like 0, maybe 30% here, 10% here, 10% here, and then again 50%. So okay, 50% here. Then you can derive your final context vector, and then this becomes your sentence representation. So it's exactly the same thing. The only thing that changed is the encoder, the thing that actually encodes the sequence one time, and then making a sequence of hidden layers or sequence of hidden vectors. So it could be RNN, it could be CNN, doesn't really matter. And sometimes, I mean, you can, the best strategy is to use both approaches. So sometimes RNN performs better, sometimes CNN performs better, and I don't think there's a clear solution, clear strategy for choosing one over the other. But RNN is such a very robust architecture. It's such a stable architecture. People just tend to use RNN. All right, but there was a paper called Wavenet, which was proposed by DeepMind back in 2016, I think, or 2016, 2017 or something. And what they did is they were encoding a classical music. It could be like piano music, it could be like a symphony or whatever. I think it was a piano music, actually. So it was a classical piano music, and you can sample. I mean, well, it's not that you sample this. The way people record classical music is they use either MP3 or whatever. They just sample at a certain, using a certain interval, like maybe 10,000 times per second, or maybe 5,000 times per second, or whatever. And of course they quantize the frequencies, but basically you can spread them out into a time series, basically. So time series, so it is a time series, just like it's a different time series than sentences like text, because they have a continuous value at every time unit, and so so you need to embed that continuous value into certain embedding, just like you would embed a text or vocabulary into embedding. You need to embed that continuous value, the pitch information, because we're talking about music. So the pitch information or the frequency information into some embedding. And then they used 1D CNN. So they used 1D CNN to encode. Well, it was something called dilated convolution, but the important thing is they use 1D CNN to encode that piano music, and then to replicate that, or maybe more extrapolate, try to predict the future future piano music or whatever. And it worked really, really well. So there must be a reason they used CNN and not RNN. So it differs by application. Anyway, okay, so moving on to transformer then. All right, maybe I can. Huh. Okay, I should have been more careful with using this spaced. All right, I'm just gonna clear everything. All right, so let's say, okay, instead of just, there's a embedding I and good boy. All right, so the I mean, there's a lot of like blogs or like tutorials or even papers of the transformer. The original paper, attention is all you need. But the core or the essence of transformer is something called self-attention, and they cite some paper to, like, justify why self-attention is a good idea, but that paper is not actually, I've never heard of that paper. But self-attention itself is a very nice idea to encode a set of tokens, and let's the 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 essence is that when you want to encode a sequence, not just sequence, some set of things, like just a bunch of encodings. It could be a set, an order set, or it could be a sequence or whatever. Just let's say that you have a set of things, set of tokens, set of words, or a set of diagnosis codes, or a set of whatever, a set of something, and the number of the elements, the number of the members of that set is unknown. It could be 10,000, it could be 5, it could be like 6, or it could be 1. So you want to have an architecture or model that can treat that is flexible enough to be applied to any number of unordered set of things, basically. And the best approach is to assume that everything is connected to everything else. So I is connected to everything else. So when I say connected, you're basically, I is attending to, of course, itself, and then it is attending to M, it is attending to all, it is attending to good boy, like this. So this is the attention that I is giving to everything else, including itself. So there's a attention that comes out of the I token. Of course, then there's an attention, a set of attentions. So and they have their own ratios. So they could be like 10%, maybe 50% attending to itself, then maybe 20% attending to our M, and maybe 10% attending to then like 5%, 7, 70, 80, 90, 10, right? This, like 5%, 5%, 10%. So as I said, it's the same thing as the classical attention. So it is attending. I is attending to itself, including itself, to all the other tokens, and the ratio or the percentage is determined by another function. There should be an attention function, and this time the attention function is basically what should it receive? It should receive its attention function. Let's say FA. Attention function receives the embedding of itself and embedding of itself. So because it is attending, first of all, it is 50% of the time. The attention strength applied to itself is 50%. So it means that Fi, I is 0.5, and Fi, M is 20%. 20%. Fa I, A is 5%. 0. Okay, this is very confusing. 0.5, so on and so forth, until the function input I, the period is 0.1. So you have a separate attention function that calculates the attention strength for each connection or for each edge. And in the same spirit, let's all right, yeah, there's no selection and drag option here, so I always have to erase this thing and then just rewrite everything together. That was unfortunate. All right, and just like I was attending to everything else, M, the second token, should attend to everything else, including itself. So M is attending to itself. M is attending this way, this way, this way, this way, this way, and of course there should be a set of function value, function outcomes like M, comma I, F, M, comma M, F, A, M, comma all the way to F, A, M, comma dot. Right. And intuitively, you would think that you would think that this value here and this value here should have the same strings. So M is like attending to 20% here, 30% to itself, something like this. Like different, of course, everything would be differently, will have different ratio, but you would think that FAI comma M being 20%, and based on that, maybe FAM comma I should also have 20%. So that's a reasonable approach. I mean, that's because it is basically the attention function FA. What it is doing is basically it is just calculating the compatibility or the the connection strength between a pair of embeddings or pair of latent representations. So FAI comma M should maybe it should be like commutative. FAI comma M should have the same values as FAM comma I, but which is not actually true though. In the actual transformer implementation, they can be different. Like this could be 10%. It doesn't really matter. Like, yeah, I mean, it is not completely commutative in the actual transformer, but intuitively it can be. It's up to you. So it's a design choice. Anyway, so you have a set of attentions coming out of I. You have a set of attention coming out of M, and of course you would have same like set of attention coming from A, like attending to itself, all the other good, boy, and the period. So there should be 6 set of attentions coming out of this encoding process. So if you, let me actually add a new slide. Oh, it doesn't really matter. Either I need, okay. All right. Okay, let me just erase all of this here. All right, so how many attentions come out of one embedding, one token? It's 1, 2, 3, 4, 5, 6. So 6 attention scores or 6 attention proportions or ratios come out of a single embedding or single token. And we have, of course, 6 tokens. So what we have is actually a 6 by 6 matrix of attention map. So we need 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And this is I am a good boy. Dot. I am a good boy. Dot. Right. So let's say that I'm gonna represent this attention strength as a matrix, and each row, a single row corresponds to the attention coming out of each token. So as I said before, this was 0.5, this was 0.1, 0.05, 0.05, 0. How many? 6, 7, 0.1. Maybe this is 0.2, 0.3, 0.1, 0.1, 0.1. So that's like 5, 6, 7, 8, 0.2, so on and so forth, basically. So you can record the attention strength and then maybe represent this as a map, right? So this will be your 6x6 matrix of attention map. So let's call this. This is the attention map. And what you would do is, of course, once you have the attention, then you need to like the reason that you're actually deriving this attention is to mix the tokens, and then derive a single fixed size vector, which was the context vector in the bidirectional RNN case. But here, well, we can call it the context vector again. But anyway, so let's say that. So how do I multiply this? So so let's say there's a I am good boy dot. As I said, the reason that you're deriving the attention is to mix the tokens according to a specific ratio or according to a specific percentage. So you have the percentages coming out of I token, which is the first row. So you multiply this to here to your embedding, so you multiply, and what do you get? You get 50% of I, 10% of M, 5% of 5% of good, 20% of boy, and 10% of the period. And you add them to you. So all right, okay. Just one time, I'm gonna be very specific. I plus 0.1 times M plus 0.05 times plus and plus and plus. Okay, then the end is 0.1 times the period, and then you have a context vector, right? So that all right. So this is how you get a context vector using the first row and the embeddings. And of course, you don't have just the first row. You have the whole set of attention maps, attention percentages coming out of each token. So you did this for another 5 times. So you multiply the first row, you multiply the second row now to the embeddings, and then you get. Okay, I'm gonna erase this. Erase this. So you will get context vector coming out of the I's attention. Then you have a context vector coming out of context vector by multiplying the second row, which is the attention strength coming out of M, and then you multiply that to all the tokens, and then you get another context vector, another convex combination, and then you have another convex combination, and another, and another, and another. So you have 6 convex combinations, and accordingly you have 6 context vectors. And this here becomes your new embeddings or new representation vectors for your sequence vector. For your sequence, for your text. So you can understand that what we did right now is extending the original attention mechanism by applying it to every single token, using every single token's attention proportional or attention percentages. So this is the essence of self-attention, and the specific implementation it varies by application. It varies by like the model choice and everything. But let's just take a look at the most basic operation, which is called QKV operation. So QKV operation. This is it's called query query key vector or something. It's QKV operation. So when you're doing this, when you're multiplying, when you're deriving the attention function, attention map, and when you're multiplying tokens and then finally deriving the context vector, you want like for example, these, as I said, FAMI and maybe it should be the other way around. I comma M and M comma I. Intuitively, they should be the same thing, but if they're the same thing, then the power of this attention map and power of this encoding process is limited. If you assume that this should be the same, they should be equivalent, then the expressiveness of your model or your encoder is limited. You want your encoder to be as expressive as possible, so that the attentions coming out of the I should capture something very different from the attention coming out of M. And of course, in the same spirit, attention coming out of A, good boy, dot. Like each attention strength or the percentages should be very different. It shouldn't be bidirectional, or it shouldn't be like commutative, basically. Commutative being like this. So in order to capture the very like fine-grained nuance of your text or of your sentence, you want to maximize the expressiveness of your self-attention process, and QKV operation allows you to do that. And maybe it is too expressive, but at least it's the most general implementation. So okay, so we'll take a look at the QKV operation. All right, let me just grab a cup of water. All right, do I have a QKV here? Yeah, right. So this is maybe it is a too simple approach. QKV. All right, give me a second. By the way, any questions so far regarding the self-attention, this encoding process? I guess this is just too basic information to some of the students, so I apologize. All right, back to here. I want to retain this figure as long as possible. So how do I do that? All right, give me a second. Let me just think about it. So I'm going to erase all the arrows first. All right, that wasn't so bad. All right, so in order to not enforce the commutative property here like this, what the original authors of Transformer or Attention is All You Need paper is, what they did is they used something called, which is very unfamiliar, which I was very unfamiliar with, and so they when you're calculating the attention strength coming out of I only, so let's just take turns, like we start with I and then go to M, go to A, good boy, done, and now we're at I, and I is trying to determine the attention strength or the percentages that should be distributed to throughout the other all the tokens, including itself. So when it is what you would do in traditionally is that you have a function and you would have I comma I, you would have f a I comma m. In that case, what this function looks like, both of them, what it looks like is basically just you concatenate I, exactly this, the same embedding as this. So you take this embedding I, you take this embedding I, and then you take the embedding m, and then you concatenate them, and then you push them through a hidden layer, and then you get a final like scalar value out of this, scalar value, which is some percentage. And no, actually, I'm sorry, this is not a percent. I mean, to be okay, so to be more technically correct, let me just erase this. To be fully, to be very, very accurate, so there's I vector here, there's M vector here, you have this hidden layer, and then you have subscalar value whose range is between negative infinity to the plus infinity and positive infinity. So this is some scalar value, and you do this for, I'm sorry, this should be, it should be I and I. So this is I and I, and of course in the same spirit, in the same principle, you have I and M. And then you have I and I mean, the specific implementation of this MLP, this function, is it's really up to you. It could be 2-layer. You could use 2 hidden layers. You could use 3 hidden layers. You could use ReLU activation. You can use 10H activation. Doesn't really matter. It depends on your preference. But the important thing is that it is embedded in somehow it is embedded through a hidden, like a nonlinear activation function. I mean, nonlinear transformation, and you get a set of scalar values, and you do this for 6 times. So you have 6 scalar values. You have 6 scalar values because you have 6 tokens. So I am a good boy dot. So there's 6 tokens. So you take those scalar values, and then put them through a softmax. And why do we put it through a softmax? Because we want to do a convex combination. We want the attention strength, like attention strength to sum to basically 1. So like this, like the total strength of your attention percentage should always be, of course, 100%. So that is why we take these scalar values and put it through a softmax, so that you can make them as a ratio, as a percentage. All right. So this is the basic approach. And let me erase this then. All right. So this is, and if you use this approach, then there's no way you can escape from this commutative property, because like this is here, and this is what would it look like? M I connection and like this. So it's exactly the same thing. So it doesn't really matter because everything is fully connected to everything else. So basically you're calculating the same thing, and in order, because you are reusing this embedding vectors, embedding representations. I'm sorry, the token embeddings or token representations, and you're directly putting it through this attention function here. And if you do this, then there's no way you can escape this destiny of commutative destiny. So what 2kV operation does is they use different set of tokens or different set of vectors when they're calculating this attention. So they have a separate set of embeddings for calculating attentions only. So what they do is all right. So when you're calculating the attention strength of I and I, there's a, let's say, oh, this is too big. This is way too big. Okay, what I'm doing is I'm calculating attention strength of I, and the implementation looks like this. You take the I embedding of Q. All right, I'm going to write this Q very large, and you take I of K, and the rest is the same. And when you're doing f I comma m, you take I q mk, and the rest is the same. So the thing that is attending to, which is the main character, the I, all right, so as I said, we're going to take turns. We're going to look at I and how it attends to everything else. We're going to take a look at M and how it attends to everything else. So the thing that is being the main character here has the core is used when you calculate the attention function. When you calculate the attention strength, the main character is called for the main character. We're going to use the query vector. So that is why I'm writing the Q here, and the target, what the main character attends to, the targets, for them, we're going to use the key vector. So IQ and IK means for, so this is the main character and this is target. So even if this is the same I token, we're going to use Q for the left part and K for the right part. In the same story, we're going to use the IQ for the left part and MK for the right part. All right, MK for the right part. And you do this for all the way till, of course, IQ and dot K. And then you, of course, you embed it, and then you take this scalar values. Then you do this. Then you take the softmax. That's how you derive the first row. Moving on to the second row. I hope this is pretty clear to everybody. So what happens in the second row, or when the main character now is M token, then we first calculate F A M I, because now it is going this way, right? So F M I. Now it's before I'm gonna write. So before F A I comma M was implemented like IQ MK hidden vector, and the dot. But this time, this is fmi. This is a function mi. So mq I k like this, and then we're going to use f a m m m q m k like this, right? So you can see where I'm going at. So and then you do this for all the way to mq. I'm sorry, not m. Dot k here, and then you take all the scalar values and then get to calculate, apply the softmax, and then that's how you get the second row here, right here. And then of course you do this again, and then all the way to the last row. So if you do this, then you can obviously see that this value here and this value here would be different, because we're when you were calculating fa I comma m, we were using iq and mk to calculate to get the scalar value, and this time when you were calculating fa mi, you were using mq and ik. So it's a different set of embeddings, different set of vectors. So this way it is more expressive. So it doesn't have to be commutative anymore. So that's okay. So that's how you calculate. So using the q vectors and k vectors, that's how you calculate the attention map. So this is where you use. So if you let me erase all of this now. So when you do this, then I'm going to use q large for all the vectors, all the so there's a q set of vectors, which is I am a good boy. I am a good boy. Dot. Then there's k set of vectors. I am a good boy. Dot. So there's q and k set of vectors, and how you would you can represent, you can describe this entire attention map as attention map equals what is that? Attention map equals q. I think we have the mathematical notation here. Qk, yeah, qk transpose the gamut. Then okay, q k transpose. Actually, there should be a softmax. So softmax q k transpose square root of d. All right, so this is exactly it, because you're just multiplying q and k transpose, and so this part here calculates the compatibility or the affinity, like how the connection strengths basically between the queues and between the queries and the keys, because we were taking like I and M, I and good, like that. And then this part here is just for a normalization vector, kind of like a normalization vector. So D is, I forgot what D. I think it's the. I'm sorry. I think it's either the embedding size or the number of tokens. I forgot which was which. Yeah, give me a second. Actually, I forgot what it was. Hmm. So let's see, DK is. All right, yeah, it's the dimension. Okay, I'm sorry. So it's the size of the embedding. I'm sorry. You divide this QK transpose by the square root of D, which is the size of, it's actually DK. So it's the size of the key vectors. So a key vector could be like 6 by, so the embedding could be like 128 or something. So in that case, this will be square root of 128. And then, of course, you need to, and then as I said, you take the scalar values out of this QK transpose operation, then apply the softmax. So this is the softmax operation. So this attention map here can be represented as mathematically formulated as this. So this is this. And then I said QKV operation. So you multiply actually V is here, which is this. This is V. The embedding vectors. So QKV operation, and then you get this. Right. Yeah. Anyway, so this is called the QKV operation. Well, I'm not sure if people call it QKV operation, but just what I call QKV operation. So you have the Q and K and V, and then that's how you get the context embedding. You just mix everything with each other using different percentages, and then get a very powerful context vector. Right. So, and then just to draw the maybe transformer architecture a little bit more in more detail. So let me just here. Okay, I'm gonna. All right, let me just erase everything. So we have I, M, good boy, and a transformer block. Transformer block looks like this. So let's see. So there's the attention part, which I'm going to call it the self-attention part. So there's a self-attention part. First, okay, so there's a self-attention part. Oh, this is wrong. So this is the QKV operation. QKV operation. And after you do this, then everything goes in here. It goes in here, and then you get the same number of context vectors out of it. And then you have, so this is the this is context vector out of the self-attention operation or the QKD operation. And then you have a couple of MLP blocks, feed forward neural network. And this is, actually, this is the same MLP actually. So I'm gonna just go through the same. Multi-layer feed forward neural network. I'm gonna FFN, feed forward neural network, and then you get the same number of tokens out again. And that's how you, and then there's, I think there's a residual connection somewhere. So I think there's a residual, like a skip connection. If you guys are familiar with the ResNet, then there's residual connection here and here, and maybe here and here. And then there's like some normalization factors, like somewhere around, like maybe there should be like a normalization, like a normalization. Like there's a technique called layer normalization, as opposed to batch normalization. There's something called layer normalization. So I think before you do FFN, there's like layer norm, and then again, like here, before you do the ResNet, there's like layer norm again. But it's not really a game changes. Just you throw it in a couple times. So, but the important thing is there's self-attention layer here, then there's a feed forward network here, and then you have the skip connections between. Then that's how you get the final context vector out of it. So this becomes a single block of transformer or self-attention, I guess. So this is a block. And so you put your input tokens into the block, and the same number of context vectors, same number 1, 2, 3, 4, 5, 6, same number of context vector comes out of the block. So basically, you can repeat this process as many times as you want. This can be block 1, there could be block 1, there can be block 2, block 3, all the way to like block n, and this is your input. And this was your inputting, this is your sentence. And then you get the same number of context vector out of it. And then this becomes your encoding. And you can either use, so that you can employ a sequence to sequence architecture, like encoder and decoder. So this will be your encoder part. And this is, so instead of using, when you were using RNN, you were also getting the same number of hidden layers per your input token. And this transformer is the same. It's the same. You have the same, like some number of input tokens, and you get the same number of context vectors out of it, or some, like, hidden or latent representations out of it. And just like you can stack multiple RNNs, like 2-layer RNN, 3-layer RNN, 4-layer RNN, you can stack transformer like one block, 2 block, 3 block, 4 block, like n blocks. And this is this is probably, of course, this will be even more powerful than LSTM or RNN, because it doesn't assume any direction. It's just like everything else. Everything is attending to everything else. So this is even more general than RNN, because RNN assumes that a sequence is coming in, but this is assuming that a set of things are coming in. So this is actually a set encoder rather than a sequence encoder. And because of the factor, because this is a set encoder, not a sequence encoder, you need to enforce this transformer to accommodate a sequence. And the way the authors of attention is all you need. That is, they employ something called positional encoding, because this is a set encoder. Because self-attention itself is a set encoder, you need to enforce or tell the transformer that these are a sequence. Like I am a good boy, that is a sequence. So you put a additional positional encoding. But yeah, I don't think I'll have time to get into detail. But basically what it is doing is it's just a separate encoding that tells that I is the first I is the first token, and M is the second token, A is a third token, and good is like fourth token. And they don't just like stupidly just sit input the number 1, 2, and 3. They use some like clever technique using like sinusoid, like sine function, cosine function to tell the model, to tell the transformer a relative position of each token in the sequence. So, but anyway, the important thing is that self-attention itself is a set encoder, and it's not a sequence encoder. And in order to make it into a sequence encoder, you need to employ a certain technique. All right, we're almost out of time now. Okay, so I'll get into the graph neural network detail and the connection between self-attention and graph neural network next time, this Thursday. All right, so if there are any questions, please shoot me. You can just type it in now, or you can shoot me an email, and I'll see you guys this Thursday. Thank you guys. Bye bye.